Hey guys, I just wanted to make a video about eigenvalues and eigenvectors in hopes to clear up some things. If you have me as your instructor, then pretty much what I'm going over is what I went over in class. But maybe if there's some parts that didn't stick, it would help to rewatch. So anyway, okay, eigenvalues and eigenvectors. Let's look at a matrix that has been kind of beaten to death in class. Okay, so here we are, and I'm going to call this matrix M. And quick little reminder on how matrices are built. So this first column here, 1, 2, is the image of the I hat vector. So what that means is, well, all right, we'll label this. This is image I hat. And then the second column, 2, 1, that's the image of J hat. Okay, so what that means is, if I were to do matrix multiplication, where I put I hat here, and then I multiply the matrix on the vector, then the way it works, I go across the first row, and I do this number times that number, plus this number times that number. So it's a dot product with the first row and this column. So that would give me 1 times 1 plus 0 times 2, and I would get 1, which actually, let's just write this in blue to really emphasize it. Okay, and then I go to the second row and I do this dot product. So that's 2 times 1 plus 0 times 1, and I get 2. And notice I picked up that first column. Okay, and so what this is saying is, and this is how I would encourage you to draw a matrix action. So if we were to put down a grid, this is good enough, doesn't really matter. And then we put down our I hat. So here it is. Okay, here's I hat. This is the 1, 0 vector. Then, so we're thinking of this as input space, and then I have to draw the output space. So when we graph a function, our input space is one-dimensional and our output space is one-dimensional, and so we can draw a graph, and we know that this value goes to maybe that y value, and we can put a little dot down there. We don't have that luxury with matrices because our input space is two-dimensional and our output space is two-dimensional, and we can't draw 4D. Can't see 4D, good luck. So we just kind of do this little matching thing. So, okay, where does that blue arrow go? Well, I won't wait for it to snap into a solid line. We'll just go for it. That blue arrow goes to 1, 2. So it goes 1 unit to the right and 2 units up. Here we are. Okay, so the blue arrow gets mapped to the blue arrow. This is 1, 2. You can also think of this as the output of M when you feed it I. Okay? And I know I should put the hat on it, but honestly, we all know what I'm talking about, so I'm not going to worry about it. Okay, similarly, if I were to draw J hat, okay, so here's J hat. This is 0, 1. Where does it get sent? It gets sent to 2, 1. 2 units right, 1 unit up. Boom. Okay, so this is 2, 1. And this is M of J hat. All right. Now, just a quick aside. It's not so important for eigenvalues and eigenvectors. I mean, well, we'll see. From here, we can build what's sometimes called a unit cell. So where I put these labels is not great. But we take this vector, and right now it's at the tail of my blue vector, and we're going to put it at the tip of my blue vector as well. So let's do that. And similarly, my blue vector, right now it's at the tail of the red, but I'm also going to put it at the tip of the red. And that gives us this little unit cell. Okay, and the reason for the vague term is because in 2D we could call it a unit square, but then in 3D we'd have to call it a unit cube, and then in 4D it'd be a unit hypercube, and you just want to capture all this notion, so we just have unit cell. Okay, and this has area 1, no big deal. And if I were to go from I to J, from I to J, that is a counterclockwise rotation. So if I were to point my fingers in I and then curl them toward J, my thumb would be pointing out towards me. Okay, so that's an orientation. The blue vector turns counterclockwise to the red vector. And notice in the image, the blue vector turns clockwise to the red vector. So this matrix M, let's write down what M was, 1, 2, 2, 1. It's orientation reversing. What used to go counterclockwise now goes clockwise and vice versa. And we can see that by computing the determinant of M, 1, 2, 2, 1. And you get 1 squared minus 2 squared, you get minus 3. Okay, so this minus sign right there That's saying that we're orientation reversing. Okay, let's draw the unit cell in the output space. So I take my red vector, which is 2 units to the right and 1 unit up, and I take my blue vector, which is 2 units up and 1 unit to the right, and I just attach them at the tips of the opposite color. And now I get my unit cell, but this is sort of a unit deserves being quotes. Typically unit means 1. And this is a single cell, but I don't know, I would think like unit area, but this does not have unit area. In fact, it has area 3, and we know it has area 3 because that's the other property of the determinant. The fact that that number there was 3 tells us that this area here would be 3 if you were to add it all up. And it's kind of believable from looking at it. You know, it has that one big square in the center right here, and then you can kind of believe you can make up another few. Okay, so we haven't talked about eigenvalues and eigenvectors yet. But, okay, so the determinant of a matrix gives you the signed area. And this is really useful, just as an aside, if you're trying to find eigenvalues and eigenvectors. So if I'm trying to find the eigenvalues and eigenvectors of our matrix here, then to be an eigenvector means if I do this multiplication, what I get is a perfectly scaled copy of my original vector. Okay, so let's do some examples and some non-examples. So look, I know that the vector 1, 1 is an eigenvector, and let me just show you what I mean. So if I feed this matrix the vector 1, 1, okay, so what does that mean? I go across this row and down this column, and I do a dot product. 1 times 1 plus 2 times 1, so I get 3. And then I do the next row. Okay, so 2 times 1 plus 1 times 1, I get 3. And this is 3 times the original vector. Okay, so these two things have to match perfectly, my input vector and the output vector. And then this matrix, when it acts on that vector, it acts like just rescaling it. Okay, this is not true of every vector. Let's just change the vector a little bit. So if I do 1, 2, 2, 1, and now I feed it, say, 2, 1. Okay, I mean, we've already seen it up here. So this vector and that vector, so my input to my output, not the same. I cannot write this as some constant times 1, 0. Can't be done because that looks like C0, and so this 0 here will never be 2. Can't happen. So this vector, my I hat, is not an eigenvector for my matrix. Okay. Oh, well, we'll just let that be. All right, so I don't actually need the other example. We've seen the other example. So how can we find these eigenvectors? Okay, so this thing. Now, look, normally we use lambda, so I'll change this to a lambda. Okay. So this is what it means to be an eigenvector. Okay, when I say this is what it means that if you multiply the matrix by that vector, you will get a scaled version of that vector. Okay, and this is your eigenvalue, and this is your eigenvector. So really quick, let's just talk about how to find them, but that's not the point of this video. I just want to say that, so this equation is of this form. Matrix times vector equals scalar times vector. And you could write that as putting the scalar on an identity matrix times the vector. And you can subtract the right-hand side over to the left. So now you have m vector minus, and then that lambda identity matrix vector is equal to the 0 vector. And you can factor the vector out, and you can write this as m minus, and the way we tend to write this is lambda I v equals 0. Okay, so this boxed equation and this line here are saying the same thing, and the one on the bottom, that's kind of a big deal. That's what you want to think of as the eigenvector equation, and sort of floating in the background with all of this is that the vector you're using is not the 0 vector, okay? Because notice if you plug in 0 and 0, then when you do your dot products, you're always going to get 0, and so indeed, if you plug in 0, 0, you will get 0, 0. But that's true of every matrix, which is why we don't care about it. It's not special. It's not an eigenvector. It's just the 0 vector doing what it do, okay? So, all right. Because our vector is non-zero, what this is saying is if you think of this object as one single matrix. So, for example, if I were to write out what it looks like, our matrix M, I have to take away lambda from the main diagonal. So, my 1s are on the main diagonal, and the 2s are off, and so on the main diagonal, I take away lambda. Okay. Okay, this is this matrix. Okay, and when I multiply it by this vector, I'm supposed to get the 0 vector. Sorry, we get really sloppy with 0 in mathematics, and you just kind of have to know from the context whether we're talking about a vector or a number or a matrix or a function. Okay, so this is a little tricky because at first glance, if I wrote this in equation form, it's 1 minus lambda v1 plus 2v2 is equal to 0, and 2v1 plus 1 minus lambda v2 is equal to 0, okay? And this is really tricky because you have 3 unknowns and you only have 2 equations. All right, so what are you supposed to do? Well, it turns out, and if you haven't had linear algebra, which is the majority of us, there's no reason you would know this, but this boxed equation, this starred equation, it's saying we're taking a non-zero vector and our matrix, which when I say our matrix, I don't mean M, I mean this whole M minus I lambda, okay? So this new shifty matrix, whatever, it sends V to 0. So this matrix sends V to 0, okay? Which means we collapse a dimension. The line where our vector V lives, okay, it turns out if I put little c's in here, it'll still get sent to 0. So really this entire line, boop, gets collapsed down to a point. So this matrix collapses a dimension. And if we go up here for intuition, here I have a 2-dimensional input. If I were to collapse a dimension, which is not happening on what's drawn, but that means all of the outputs would lie on a single line. And I just want to go back to this determinant tells you the area. Well, the area of a line is 0. And the same thing happens in higher dimensions. In higher dimensions, you sort of have this unit cube. And if you were to collapse a dimension, you'll get some kind of, oops, so much for that. Okay, unit cube. And if you collapse a dimension, I was trying to do like a parallelogram. Good enough. Here there's no volume, and here you have volume, right? Even though there's area, we don't care about area in 3 dimensions, we care about volume. And in 4 dimensions, we care about hypervolume, and so on and so on. So when you collapse a dimension, your determinant will be 0, because the determinant tells you the area, or the volume, or the hypervolume. And if you're in 2D space, you had better have area. If you're in 3D space, you better have volume and all that stuff. So if you collapse a dimension, you're going to lose it. It's going to go to 0. It's just like how a line has no area, right? And this has no volume, and so on. Okay, that's how we get our third equation. So we have 3 equations, and the third one that's floating in the background all along is that the determinant of m minus lambda I is equal to 0, and that is because m minus lambda I collapses a dimension. Okay, that is what this equation is saying. So it was implicit in the equation. It's saying, hey, look, I'm collapsing a dimension, but if you haven't had linear algebra, you would never know that that's what this is announcing to the world. Okay, so this is our third equation, and it's where you start in finding eigenvalues and eigenvectors. So let's go ahead and start there. Okay, so here's m minus lambda I. Let's take the determinant of it. Okay, 1 minus lambda, 2, 2, 1 minus lambda, boom, boom. Okay, determinant. I do the product down the main diagonal minus the product in the off diagonal. And we are going to set this equal to 0 because that's what we're trying to find. Okay, so that says 1 minus lambda squared is equal to 4, and we square root both sides. And we have 1 minus lambda is equal to positive or negative 2. And then solving for lambda, we're going to get lambda is equal to 3 or negative 1. Okay. And so we actually already saw, hey, look, here's lambda equals 3. Okay. But let's just keep going and let's find this proper. So, all right, you always start with this equation here to find your eigenvalues. Then once you have your eigenvalues, you can plug them in. And so 1 minus 3 is a negative 2, and then I have a 2 and 2 and negative 2. All right, and this multiplied by v1, v2 is equal to 0, 0. And in equation form, look, the whole reason we did this, the whole reason we found these eigenvalues is because we're going to get redundant equations. So if I wrote this out in equation form, it says negative 2v1 plus 2v2 is equal to 0, and 2v1 minus 2v2 is equal to 0. Okay, so notice that the second equation is just the first equation times negative 1, which means there's no new information. If we know this first equation is true, then multiplying by everything by negative 1 is still true. So there's nothing new here. So we can just focus on this first equation and think, okay, what is it telling me about v1 and v2? So I'm going to move this thing over to that side, and I have 2v2 is equal to 2v1. And if you divide out the 2's, that says v2 is equal to v1. So now, to find an eigenvector, you just choose numbers that satisfy this. So I chose 1 and 1, but you could also choose pi and pi. You can choose negative 17 and negative 17. Okay, all of these work. All of these are eigenvectors for the eigenvalue 3. And all of them look like whatever number. You just have to repeat it. Okay. So typically you want to choose nice numbers. You want to choose small numbers, whole numbers, stuff like that. When MATLAB gives you eigenvectors, it will normalize them. So what does that mean? For example, here we are. The norm of this vector is when you square each component and then take the square root. So I have root 2, which really just means it's the length of the vector. If I go over 1 and up 1, this is root 2, right? So what MATLAB will tell you as the eigenvector is the normalized form, which is when you divide everything by the magnitude. So it will give you this, which is going to look like 0.71, I think 7 stuff, 0.717 stuff, okay? So it won't be so recognizable, but you should be able to glance at it and go, oh, this is 1, 1, because these are the same, okay? So that's just an aside about MATLAB. All right, if you go through the same process for lambda equals negative 1, then the vector you come up with is, again, you can always rescale, but something like negative 1, 1. Right? And what do I mean by always rescale? Look, if I multiplied this by negative 1, I'd have positive 1, negative 1. That also works. If I multiplied it by 17, I'd have negative 17, positive 17. That also works. It's just the first and second entries are negatives of each other. So if the first entry is positive 1, the second entry is negative 1. But if the first entry is negative 1, the second entry is positive 1. So that's what I did here. Okay. So we have eigenvectors, boom, and eigenvalues, bang. All right, what does this all mean? So this is what I wanted to get to. All this original spiel is because I'm sure we're going to take spring break as a break, and I encourage you to do that. But when you come back on Monday, oh no, that stuff is due Tuesday. So this is kind of showing you how to find eigenvectors and eigenvalues in case you haven't started yet. All right, let's talk about why. I guess this deserves a question mark. Okay, so let's get a new page. All right, it turns out that our matrix 1, 2, 2, 1 is equal to, and then it's a product of 3 matrices, okay? And this matrix here is a diagonal matrix. This matrix is not, I'll call it V because it's going to be our eigenvectors. And then this is V inverse. It's just the inverse of the matrix, which, I know we also haven't really talked about. So we'll get there, but just bear with me. All right, so the way we're going to build this product, you put the eigenvalues on the main diagonal, and the order does not matter. I just chose to put the positive 1 first. It truly does not matter, okay? And then this is a diagonal matrix, so everything off the diagonal is 0. Okay, now here's what matters. Since in the first column I put 3, in the first column of my eigenvector matrix, I need to put the eigenvector corresponding to 3. And so I went with 1, 1. And again, you could do 17, 17. You could do 1 over root 2, 1 over root 2. Okay, it's just, you have to choose one, and then once you choose it, go with it. Okay. Now for the negative 1, I'm going to do the eigenvector corresponding to negative 1, and there it is. And then we need to do V inverse. Okay, so what the heck is V inverse? Well, I guess we're not ready to get to Y just yet. So let's do an aside. And look, there's plenty of videos online talking about how to invert a matrix. So I'm not going to go into great detail. I'm just going to show you the algorithm. I'm not going to explain it very well. And apparently my iPad's going to freak out on me. Okay, so here's what you do. You put the matrix that you want to invert, and then you put the identity on the other side. And this is just some augmented form. Okay, so in general, it looks like this. We have matrix we want to invert, some bar to let us know where it stops, and then the identity matrix on the other side. And our goal, we want to transform this bad boy into something that has the identity matrix on the left side, which actually, look, we're still new and fresh. Let's write out what we mean. We want that to appear on the left side, and then we don't care what's on the right side, but it turns out that thing that's on the right side is going to be V inverse, okay? So we want to, here's our start, and this is what we want as our finish. So that's the goal of the game, but what are the rules of the game? Okay, so the rules are we have to use elementary row operations. Elementary row operations. What a mouthful. There's three things you can do. You can add or subtract. Oh, sorry. This is the most common one. Add or subtract multiples of one row to another, right? Importantly, that says one row, not 7 rows. You get to pick one, you get to rescale it somehow, and add it or subtract it to another. All right, let's see an example of that. So I have this as my starting point, but I want that. And the way this game is always going to work is you're going to go down and make the first column match first, then the second column, then the third column, then the fourth column, and, well, whatever. Let's get there first. So I have a 1 and I need a 0. So what am I going to do? I'm going to change row 2. My new row 2 is going to be my old row 2 minus row 1. Okay, I'm subtracting a multiple of row 1 from row 2. Okay, this is that first type of elementary row operation. So importantly, I'm not changing row 1. Row 1 stays the same. That baby's not getting changed. Okay, but row 2, I have to subtract row 1. So 1 minus 1, 0. 1 minus minus 1, 2. 0 minus, okay, negative 1, and 1. There we go. We did it. So going from here to here, we did this elementary row operation. All right, there's another type of elementary row operation. There's 3 types, sorry. Okay, there's 3 moves in this game. I've just shown you one type of move. You can also rescale a row. Okay, so let's do that. You know, I look at where I am, here's where I am, and here's where I want to be, and column 1 looks good. Column 1 looks good, so let's go to column 2, and this 2 is an issue, and I want to become a 1. So I'm going to say, okay, row 2, and where the arrow points, that's my updated row. So I don't need to write new and old. We know this side is the old side, and this side is the new side, okay? So I want to rescale row 2 by multiplying by a half. So row 1 stays the same. I'm not changing row 1. Okay. Row 2, I multiply everything by a half. So 0, 1, minus a half, and a half. Okay, sweet. And now I look at where I am, and I look at where I want to be. And we see this 0 here is what I need. So I need to attack that. And it's finally time to update row 1. So row 1 is going to be the old row 1, but I'm going to add row 2 to it. That way I can add this one here and kill it. All right. So here we go. We have 1, 0, 0, 1. I've added it. I've killed it. Okay, now I have 1 plus a negative a half. There we go. Oh, and row 2 stays the same. Let's just fill in row 2 really quick. Okay, and then 0 plus 1/2. I get 1/2. Okay, so it turns out this is V inverse. Okay, and what does that mean? Oh, and I should also tell you the third type of elementary row operation. So the third thing you can do is swap 2 rows. Okay, and the main reason you would do this is, like, let's say you were beginning, and it doesn't really matter what the rest of this matrix looks like. Just pretend for a moment that I have a 0 right there, and then on this side is supposed to be the identity. My goal is to go from this object to an identity, which means this 0 has to magically become a 1. And notice, none of these elementary row operations say you can just, like, add 1. Okay, you can't do that. You're always adding rows to rows. So I can never magically make a 0 non-zero. I cannot rescale a 0 to a 1. Can't happen. So what I would do is I would just swap these two rows, and that's when we would use this type of thing. But, okay, doesn't matter for this. All right. So here's V inverse. What does that mean? It means if I multiply V and V inverse, and it doesn't matter what order it's in, I will get the identity. So let's see that happen. So I'll do V inverse first because I'm staring at it. Okay, minus a half and a half. And then let's fill in V. Okay, and let's see what happens. So I go across this row and down this column, and I do a dot product. That's a half plus a half. I get 1. Sweet. Oh, you know what? Here's what I should do. I should say I do this row and this column, and that gives me this entry. All right. And now I'm still in the first row, but I'm going to go to the second column, and I do a dot product. So it's 1/2 times -1 plus 1/2 times +1, and what you're going to get is 0. All right. Now let's go down to the second row, and I'm going to go back to the first column. And so second row, first column, that's going to be here, second row, first column. And I have -1/2 times 1 plus +1/2 times 1. I get 0. Okay, I'm still in the second row, but now I'm going to go to the second column. So second row, second column, that entry is going to be here. I have -1/2 times -1. Oh, so +1/2 plus another +1/2. I get 1. All right, so yes, indeed, we got the identity matrix. And what this is saying is that these two matrices undo each other. And by undo, look, we want to think of matrices as moving around space, okay? So they take an input that looks like this, and they output something that looks like this, okay? And so here's M, it goes like that. The thing that is M inverse would do the opposite. It would take this blue vector here, and it would send it to this blue vector here, okay? So anyway, great. So let's fill in this object, and then let's talk about why this is so great. Here's where I really wanted to get to in the video. So if you're just now joining because you didn't want any of that review, that's totally fine by me. All right. Here's the deal. A diagonal matrix is super easy to understand. Okay, let's do input-output for a diagonal matrix. So if I input my I hat, okay, remember the first column tells you the output of I hat. So where that's going to go, I kind of gave myself more room than I needed to in the first one, is 3. It gets stretched by a factor of 3. That's it. Okay, so this is 3, 0, and it came from 1, 0. Okay. All right, let's play the game with j hat. So here's j hat, and it goes to negative j hat. So here it is. Boom. All right. So it just gets reflected over. So 0, -1, and it came from 0, 1. All right, but because we know this, we also know where things like, let's go, well, that's going to be pretty big. We'll do this one. Why did you, okay, try it again. We'll do this one. There we go. So this vector, okay, this is -1 copies of I and -1 copies of j. Okay, so this is my -1, -1 vector. And where it goes is negative the blue vector plus negative the red vector. So negative the blue vector, 1, 2, 3, and negative the red vector here. And if I add them, I just do tip to tail, I'm going to end up right here. Okay, so boom. What are the coordinates of this? This is -3, +1. And we can check. We can check and see if I'm lying to you or if I'm telling the truth. If we take our, oh, sorry, so what are we doing here? This is this diagonal matrix. So it's 3, 0, -1, 0. We can just multiply 3, 0, 0, -1. Let me silence that. Okay. and we have minus 1, minus 1. And if you go across a row, down a column, across a row, down a column, you will indeed get negative 3, positive 1. Okay? So this is why once you've drawn these two vectors, you know where everything else goes. Because the combination you would use of blue and red is the same combination you use of blue and red. It's just that now my blue is stretched and my red is flipped, but that's okay. So let's do it again. Let's get some practice. So I'm going to be, let me change the color. I'm going to be up here. So this is 1 copy of blue and 2 copies of red. Okay, that's what those coordinates are telling us. So it's going to go to 1 copy of blue plus 2 copies of red. It's going to go right here. Okay, so this is where the diagonal matrix will send 1, 2. And it turns out, what is this? This is 3, negative 2. Okay. Now, we can also just see, look, if I multiply this diagonal matrix by any vector xy, what's going to happen? You go across a row, down a column, and I do that dot product. That's 3x plus 0y. Okay, so I get 3x. And then you go across a row, down a column, and you get negative y. So with a diagonal matrix, the stuff on the diagonal just tells you how to rescale each component. Okay, couldn't be easier. But the way I'm moving around these vectors, where I take these coordinates and they're telling me the combination of blue and red to use, and then I use that same combination of blue and red, but now they're stretched or flipped or whatever, that's true of every matrix, okay? So, what this is telling us, we have our matrix M over here, our original mystery thing. It's saying all that M wants to do at its core is stretch something by 3 and flip something over. Okay? This diagonal matrix behaves the same way M behaves. It's just that M does not stretch I and flip J. M stretches 1, 1 and flips negative 1, 1. So let's draw that. Okay? So I guess I'll go down like 1 more-ish, and we're over here. All right, let's draw the negative 1, 1, 1. Okay, so this is 1, 1. This is my first eigenvector. And negative 1, 1, that's negative x positive y, negative 1, 1. This is my second eigenvector. And this is kind of bad notation because previously I used v1 and v2 for components, and now I'm doing them for vectors. So maybe I should slap a little vector bar on top, but whatever. I'm trusting that you guys get it, but I'll do this. Okay. All right. So now what M does, okay, which, look, I'll write down what it is, but it doesn't really matter because we have this decomposition that says, all right, look, you're going to be 1, 1, you're minus 1, 1. And, come on now. There we go. And then this gets scaled by 3, and this gets flipped over, and then we have 0, 0, and then, stuff. Okay. So what it's going to do, here's my input space, and then let's get the output space going. Output space. Great. So it stretches the blue vector by 3. 1, 2, 3. Here we are. So this is 3, 3. This is M on V1. Okay. And it flips over the red vector. Flips it over. Here we are. This is 1 unit in x and negative 1 unit in y. This is M on V2. All right. And now we know where everything else goes. Okay. So this thing, let's draw that vector. Okay, this is the big shift. This is what I want to spend some time on now. The green vector I just drew, if I were to put down its coordinates in the coordinates we're used to, I would say this is no movement in x and 2 positive units in y. Okay? These coordinates are talking about left, right, and up, down. They're talking about I hat and j hat. You move 0 in I hat and you move 2 positive copies of j hat. Okay. Instead, let's describe getting here using v1 and v2. Okay. So to signal that that's what I'm doing, I'm going to do this like square bracket instead of these curvy brackets. Okay, so curvy brackets are ij, and square brackets are referring to v1 and v2. So in v1, v2, I claim you take 1 copy of v1 plus 1 copy of v2. So I'm just saying, if you add the blue and the red vector, you will get there. Okay, and so this is telling you how many copies. So if I wrote out, so 0, 2 is equal to v1 plus v2. That's all this is saying. I have 1 copy of v1 and 1 copy of v2, and I'll get this. But I'm encoding this 1, 1 information in this vector. Okay. Why is that useful? Because M behaves like this diagonal matrix on the blue and the red vectors. So if you can write the vector you care about using the blue and the red vector, it's very easy to talk about where it goes. It goes to 1 copy of the blue image plus 1 copy of the red image, which lands us right here, because 1 copy of the red will bring us down, right? So here we are, okay? And what are these things coordinates? Well, it's 4 over in x and 2 up in y. This is 4, 2. And we can check. Let's check. So if I compute 1, 2, 2, 1, and I fed it 0, 2, then, okay, across a row, down a column, 1 times 0 plus 2 times 2, that's 4. And across a row, down a column, 2 times 0 plus 1 times 2, that's 2. It worked. Okay, it worked. This is why we love eigenvectors and eigenvalues, and this is eigenvector decomposition, or it's also called diagonalization. Okay. And it's because this middle diagonal matrix is telling you how your original matrix wants to behave. Like it just wants to stretch and flip something. That's it. And what are the somethings? Well, it wants to stretch that and flip that. Okay. All right. Now let's uncode this object here a little bit more and see how all of this stuff comes into play. So my claim is, actually, we're going to look at this. Okay. But we're not going to compute it the way I just computed it. We're going to use this diagonalization. So this is equal to bang, 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 0, 2. All right. And this is 1, 1, minus 1, 1, 3, 0, 0, minus 1, 1 half, minus a half, 1 half, 1 half. Okay. So this is just here. This is this thing. Okay. And let's see what happens. So think of this like function composition, like if I had f of g of h of x, then you first compute h of x and you feed that into g, compute all that, feed that into f, okay? I know you all have done function composition before. And so when I say think of it like that, what I mean is we first compute this, and that'll give us a vector, and then we're going to feed that vector in that matrix and so on, okay? So let's do it together. So I can copy and paste everything else, minus 1, 1, 3, 0, 0, minus 1. All right, now let's compute this. So I go across a row and down a column. 0 times a half plus 2 times a half. I get 1, which let me actually write it like this. 1. And across a row, down a column, we get 0 plus 1 half times 2. We get 1. So 1. And I'm going to use square brackets just to emphasize what the heck just happened. Okay? This matrix is a translator. Okay? Here we have I hat, well, okay. What the 0 and the 2 mean is they mean you take 0 copies of I hat plus 2 copies of j hat. And what this matrix does is it translates it, and what this is saying is you take 1 copy of the first eigenvector and 1 copy of the second eigenvector, and you'll be at the same point. This is exactly what we were talking about up here. Oops, didn't mean to do that. So this first matrix, this V inverse, does that computation for you, okay? And then this next computation, this is doing exactly what I gestured with my hands over here when I drew that vector, okay? And all right, so let's do this next thing. So we have 1, 1, minus 1, 1. And here we're going to get 3 and 1. And these are still technically in the, oh, sorry, negative 1. Okay. This is still saying you'd be 3 units of V1 minus 1 unit of V2. Okay, in other words, where are we? Here we go. Here's V1. So we need to do 3 of those. 1, 2, 3. And then we have to do negative of V2. So we go to negative of V2. And that's exactly the pattern. 1, 2, 3, negative of V2. That's how we got this thing. Okay. And it's in square brackets because we're still thinking in terms of V1 and V2. But what does this matrix do here? It translates it back. Translates back to I hat and j hat. Okay. So when I do this computation, I have 1 times 3 plus negative 1, negative, so plus 1, I get 4. And then 1 and 3, 1 and 8, I get 2. Right? And so we got 4, 2 again, which is exactly what we should get. So, all right, eigenvalues and eigenvectors, they let you decompose your matrix into a diagonal form. Now, there's a lot that I'm not saying there because it's not always true. There can be some bad matrices that you can't do that with. But when you can, man, is it great. And this is why it's great. It's because you get to realize, oh, I wasn't supposed to be thinking of I and j. I was supposed to be thinking of V1 and V2, and then all I have to do is stretch something, maybe flip something, you know, stuff like that. So it just makes this mystery matrix so much easier to understand. Okay. All right, that's all I have.